Our next speaker is Even-Zohar, and he is going to speak on the BCFW tiling of the
Amplituhedron.
Thank you.
Yeah. Okay. Thank you very much. Thank you for having me, and it's really fun to be back in Davis. So I will start with a very quick review of the totally non-negative Grassmannian. So the Grassmannian is all, we are working over the reals. The Grassmannian is all k-dimensional vector space in an n-dimensional vector space, and then the totally non-negative Grassmannian are all those points in the Grassmannian where all the n choose k Plucker coordinates are non-negative. So this means, for example, if we have this 2×7 matrix whose vector space is just its row span, then this means that all the 2×2 determinant, like this one, for example, the 2,4 Plucker coordinate, you can see it's a non-negative, and you can check the other ones. So this is a point in the totally non-negative Grassmannian. Now you can partition the totally non-negative Grassmannian into what's called positroid cells, which are determined by which Pluckers are strictly positive and which Pluckers are zero. So we denote them by SM, where M is a list of those that are strictly positive. So again, here's an example. Let's say that we want 1, 2, 1, 3, and 1, 4 to be strictly positive, 2, 3, 2, 4, and 3, 4 to be 0. So it turns out to be that these are exactly all points in the totally non-negative Grassmannian of this form. So you can see that they have this is a very nice piece of the Grassmannian. It's parameterized by 2 real numbers. And it turns out that all of these pieces are nice and simple. So this is what Postnikov showed, that this positroid cell gives a Grassmannian a structure of a cell complex, and each one of these cells can be parameterized similarly, and it has some dimension d, which is called the dimension of this positroid cell. And there's also a lot of combinatoric I'm not going to say much about, but you can index this collection of positroid cells by matroid, by planar bicolored graphs, by decorated permutation, by binary valued tableaus, and even more. Okay, so now let's define the Amplituhedron. This was discovered by Nima Arkani-Hamed and Yaroslav Trenka, which are two physicists in Princeton and Davis. And in order to define it, I have to fix a metric. So there's a new parameter m, and the matrix is going to be n by k plus m. It's going to be a positive matrix in the sense that all its maximal determinant with k plus m by k plus m are going to be strictly positive. And since we're fixing it, you can have in mind just a particular metric, such as van der Monde matrix. And now this metric induces a map from the totally non-negative Grassmannian to another Grassmannian, the k times k plus m Grassmannian. And simply what we do is we multiply from the right by the matrix Z. So it is a lemma that this is a well-defined map, so that the image has full rank. So now the Amplituhedron is defined to be the image of the totally non-negative Grassmannian under this map. So it's some subspace of the k plus m Grassmannian. Right, so that's the definition. Here's the definition again in one line, and let's mention some facts about the Amplituhedron. So as we said, it's well defined, it's compact, it's connected, it has full dimension in its ambient Grassmannian, which is k times m. Many of its properties do not depend on the fixed matrix Z. And it was suggested that its volume, in some sense, I'm not going to say much about, gives a physical quantity, which is a scattering amplitude, which is more or less the probability that a certain scattering occurs when some particles collide. So traditionally, these scattering amplitudes were computed completely differently as a sum over Feynman diagrams. And these are useful because these scattering amplitude can be tested and predicted and measured in the high energy colliders, such as the large hadron colliders in here. More modernly, they can be computed using the BCFW recursion, which is equivalent to the Feynman diagrams, but a lot shorter. and due to Brito, Kachasov, Feng, and Witten. And when you want to, if you want to show that the equivalence of these two physical theories, that also the amplituhedron gives you the same scattering amplitude, so one main step is to show that the terms you get from the BCFW recursion correspond to different pieces of this geometrical object that we defined, which is the amplituhedron. So this was conjectured a decade ago by Akani, Hamid, and Trenka. All right. So now what do I mean by tiling? So I want to subdivide a space. So this is a simple cartoon of tiling. So say that I want to subdivide this shape in 2 dimensions, and I know it's the image of a projection from 3 dimensions to 2. So one way of doing it is to take 3 simple pieces of the pre-image, which are these 3 faces in 3 dimensions, and each one of them maps injectedly to 2 dimensions, and together they tile this shape. So this gives a simple tiling of this shape, and now imagine on the left the totally non-negative Grassmannian, and on the right the amplituhedron. And I want to find such a tiling. So actually, they suggested such a tiling. This is called the BCFW tiling. So later, I'm going to give a definition of these tiles. But first of all, let me state the main result. So given this list of tiles, we showed that for every positive matrix Z, first of all, each one of these tiles maps injectively into the amplituhedron. So we call it a tile in this case. Second, that 2 different tiles do not overlap. So the images are disjoint of each other. And third, that the union of all these tiles together covers the whole amplituhedron. So this is what we call a tiling, and this is what we showed. So now let me mention also some known cases for the amplituhedron, for general background. So in the case k equal 1, the amplituhedron is equivalent to a cyclic polytope in projective space. For the maximal possible k, which is n minus m, it's simply the totally non-negative Grassmannian, and this is because the matrix Z is square now and everything is invertible. So you can think about the amplituhedron as some common generalization or some interpolation between the cyclic polytope and the totally non-negative Grassmannian, which are 2 well-studied objects. In the case m equal 1, now we generate n to 1, it's known that the amplituhedron looks like that. It's a bounded part of a cyclic hyperplane arrangement sketched here, and this is by Stephen Karp and Lauren Williams. And also there is a quite powerful duality between different values of k. So basically there's duality for even m, there's duality between k and its complement k. This is by Galashin and Lam. And the case of m equal 2 was much studied because it's some kind of a toy case for m equal 4, which is what physicists are interested in. And Bao and He shows that there is a BCFW-like tiling for this amplituhedron, and then these people showed there are even more tiling, and that there is a correspondence between this tiling and the triangulation of a polytope, of the polytope called the hypersimplex, and they showed even much more. And this was a paper in the previous FPSAC by Matteo Parisi, Melissa Sherman-Bennett, and Lauren Williams. Now for m equals 4, which is what we need in physics. So there's a paper by Karp, William, and Zhang with an appendix joined with Thomas, where they give many different ways of defining and thinking about the BCFW recursion and some explicit non-recursive descriptions for these tiles. And among which there is a domino matrix form, which I'm going to use later. Okay. So now let me give the definition of the BCFW tiles. So we're going to use another combinatorial object new to this problem, which is the chord diagram. So we take a line with n different markers, and we draw k chords between pairs of points on this line. And there are certain rules that we want to follow. So first of all, we don't allow any code to start exactly on a marker or to end exactly on a marker. We don't want any code to start before 1 or to end after n or to end between n minus 1 and n. So n should be actually isolated in this diagram. We don't like codes that are too short, so we don't want the code to start and end at the same segment, nor in adjacent segments. Also, we do not want two codes to start at the same segment, although we do allow two codes to end at the same segment, and we even allow another code to start at that segment, just not two starting points. And most importantly, we do not want any codes to cross. So with all these rules, there are finitely many options for code diagrams, and if you count them, you get the Narayana number, which is indeed the number of BCFW tiles. And now I can define the BCFW tiles that correspond to a given chord diagram. So let me do it by an example. So we're going to define the positoroid cell in the Kn Grossmannian, and later Z maps it to the Amplituhedron. So we need to, and we're going to specify it directly as a K by n matrix whose row span is this point or set of points in the Grossmannian. So for every chord we are going to, of the K chords, we are going to have a row in this matrix, and we look at the starting and ending point, the starting and ending segments of every chord, and then we put two variables at the beginning, alpha and beta, and two variables at its end, gamma and delta, for each chord. So this gives us 4 K variables already. For every chord that is top chord without any other chord above it, we put an epsilon variable in the last column, n. For every chord that is a child of another chord, so we look at its parent, the chord immediately above it, and what we are doing, so say for example, let's look at C3, which is the child of C1, we copy the starting two variables, alpha 1 and beta 1. Actually, we take a proportional copy and put them in the same position in the row corresponding to chord number 3. Okay, so we also have epsilon variables for the other chords. Now, what do we do in this case where with 1 and 2? So we can have a contribution of two different variables, or even of this form to the same entry of the matrix. Anyway, this is what we do. We fill in everything else with zeros, and note that every row of this matrix has either 5 or 6 non-zero entries. Okay, so this defines us a matrix given a chord diagram. Now we also put some certain rules on these variables. Some of them we want to be positive, some of them we want to be negative, and it depends on some combinatorial rules of the chord diagram I'm not going to say much about. Also, when two chords start or end at the same segment, then we have a condition on the 2 by 2 determinants that we have in these columns, and again we want it to be negative or positive according to some rules. So under these rules we get a totally non-negative matrix. So this is a point in the totally non-negative Grassmannian, and what we show is that these are exactly, those that you get from chord diagrams are exactly the BCFW tiles. So so the result is that for every BCFW tiles, we have such a parameterization. It's unique up to rescaling each row of the form of the domino matrix form corresponding to that chord diagram. And these are the BCFW tiles. So that was the definition of the tiling. And now here's an example. So for example, if n equals 7, k equals 2, and m equals 4, of course, then we have 6 different chord diagrams under our rules. Each one of them gives us this kind of a matrix. If we multiply them by z, which is 7 by 6 in this case, we get their images in the Amplituhedron, and we claim that this is indeed a tiling. Now with these parameters, alpha to epsilon, this gives a tiling of the Amplituhedron, of the 7 to 4 Amplituhedron. Okay, now in the remaining time, maybe let me sketch some proof ideas. So the proof relies much on several things. One of them is twistor coordinates. So let me remind you the notation. C is a point in the Grassmannian. Z is our fixed matrix, positive matrix. We multiply by y is going to be C times Z, which is the image. It's a point in the amplituhedron, which lives in a kk plus 4 Grassmannian. And now for every 4 indices, A, B, C, and D, we're going to define the twistor coordinate. It's going to be a function of the point in the image, in the amplituhedron, where we put this matrix Y on top, and the 4 rows corresponding to A, B, C, and D from the matrix Z below it, and take the determinant. So this is called the twistor coordinate. How to think about these twistor coordinates? So this is more or less correspond to what happens with polytopes that can be, as you know, described either as a convex hull of a certain set of points or as the intersection of a certain set of half spaces which are given by certain hyper surfaces in the hyperplanes. And here it's more or less the same. So these twistor coordinates are some functions that vanish on some hyperspaces, and these hyperspaces are what we need in order to study the amplituhedron. So for example, some pieces of the external boundary of the amplituhedron will be the vanishing locus of some of these twistors. And other twistors are going to vanish exactly on the boundary between two tiles in the BCFW tiling. So that's why these twistors are useful functions. And now let's see how this plays in the proof. So the first part of our result is the injectivity, and the idea of our proof is just to solve the inverse problem. So we take a point in the amplituhedron, and we want to find its unique pre-image in the form of the domino matrix corresponding to the tiles that we are interested in. So basically we have to recover these variables, alpha 1 to alpha to epsilon 1 and so on. Now this is easier when all rows have support 5. So if we have a row of support 5, there are some linear algebra lemmas that tell us that we can just recover these entries as 5 twistors. So this indeed gives us the pre-image. Now, what can we do if we have a row of support 6? So this happens when we have a chord and its child below it. And remember that here in the 2 coordinate corresponding to the starting point of the parent, we also have a proportional copy in the row corresponding to its child. So what we do is first we solve the top row, which has support 5 in this case, by twistors again. And now we already know the proportion between alpha 1 and beta 1. So we know the proportion between 2 of the 6 entries, and this brings us to the support 5 case essentially again. So when we do that, we get instead of some twistor, but in a specific row of the determinant that defines the twistor, we have now a combinations with coefficients that are alpha 1 and beta 1. And when we expand it, we get actually a polynomial in the twistor. So some entries are going to be expressed not as twistor, but as polynomials in the twistors. And if we have more rows and more nesting in our chord diagrams, then we'll have higher and higher degrees for these polynomials. We call these polynomials functionaries. And we have also an abbreviate notation for them. So note that they come in a really nice form, where here, for example, you have 2 monomials. The only difference is that 1 and 2 are shuffled, so we write them like that. So we have these 3 out of 4, these 3 out of 4, and 1 and 2 are shuffled between the 2. So this is a quadratic functionary. Okay, so this is how we solve the inverse problem. Second part of our result is separation. We solve that different tiles do not overlap, and the idea is to go over every pair of tiles in our tiling and to find a twistor or a functionary that separates between them. And this means that it's positive on one and negative on the other. So now there are different cases, and we have some rule of writing a twistor when the two tiles have list codes that ends at different position. Another rule of writing a quadratic functionary where the list code ends in the same position but starts in different position, and otherwise we have to work recursively on the subdiagrams below the common code. So this is basically a set of rules, an algorithm that give us the separating functionary for every two chord diagram. And as you can see, what you do is for the R part or for the L part, you take the previous separator, you do some substitutions to the indices, and you end up with a separator you actually need. And maybe a last sentence about the surjectivity. Our proof that the tiles covers everything is not very direct. What we show is that we study in detail all the codimension 1 pieces of this tile, and we show that either they go to the exterior of the Amplituhedron, or they come in pairs that are glued to each other. So everything fits so nicely, and since we know that the Amplituhedron is connected, there cannot be any other point in the Amplituhedron that isn't already covered by this set of tiles. Okay, so this is the idea of surjectivity. This is, for example, this gives you all the pairs of tiles that are adjacent. According to this analysis, there are some combinatorial rules that give that, but I think my time is over, so thank you.
Are there questions?
Yeah, so you coded the Amplituhedron by this open-end set, which is the images of these tiles. You touched a little bit on it at the end. If you take the closures of these and look at the intersections, is there a hope that there are, in fact, lower dimensional cells upstairs which, in fact, project to exactly fill in the gaps between these open pieces that you have?
So I have to repeat the question. I don't exactly know what you mean by upstairs.
Are there cells in the Grassmannian
I see.
of lower dimension which project to fill in the gaps?
I see, yeah. So we do that explicitly for code dimension 1. We do not identify all different cells in the skeleton down to 0, but in principle, we think it can be done, and actually it also seems to be something useful, so we may do it. Yeah.
But the dual graph of your finding, maybe the thing that you use, does it give you some known dual graph, maybe Mariana numbers, like the way things are put together?
So what is the question about it?
The question is the dual graph of your finding interesting, like the way it's like?
Okay. So the question is whether this dual graph is interesting. So in order to build this graph, I don't know, you tell me if it's interesting. Basically adjacent tiles are given by simple combinatorial move, which are, in the simple cases, this is shifting the start of a chord or the end of the chord. But there are also some other cases which are a bit more complicated. And so it has this combinatorial description. And then you can see what, so for example, I think it's the diameter of this graph is order of n times k. Yeah, you can say much about this graph by its combinatorial description. Okay. Yeah. So this is actually okay. So the question was what happens with higher values of m, and for some reason, even m is simpler and more interesting than odd m here. And it turns out that this is work in progress. So we are working on that. It turns out that when you go to m equals 6, for example, or 8, then you have a totally different new phenomena. So it's similar to the jumps that you have from m equal 2 to m equal 4. So certainly there are new phenomena. We need new idea. It's not a straightforward generalization.
One quick question. Carl.
Have you looked at the case m equals 3?
And not so much. The question was about the case m equals 3. So no, actually, we looked at it a little bit, not so much. But again, I think there are also some phenomena that happen there and not in m equals 4. So the case m equals 3 is also going to be interesting, maybe in other ways.
If there are additional questions, I'll ask that you ask the speaker during the coffee break. Let's thank the speaker once more.
Thank you.